Something that steps a little bit beyond what we've looked at previously in Year 10 Science and other levels. We're going to look at the electronic structure of atoms and take our electron configurations just a little bit further to give us a better idea of how that relates to the energy, the way that the energy levels are arranged inside an atom. So let's get started. So these are the things that we need to be able to do after we've looked at the electronic structure of atoms. Okay, so we need to be able to talk about emission spectra, explain the difference between shells and orbitals, calculate the maximum number of electrons per shell, which a number of you can hopefully already do, draw electron shell diagrams for elements according to the Bohr model, which is the same model as what we've already seen in Year 10, define the term ionization energy, understand that chemical properties of atoms are defined by their electron configuration, and then these new ones here, looking at the actual subshell notations for elements up to 36. So we're going beyond the first 20 and look at our exceptions for chromium and copper. This one's probably going to take us a little while, so let's get started. So when we talk about atoms, and excitation, we're essentially talking about flame colors and the different colors that we see. So when we heat atoms, they give off light of particular colors, and this is because the electrons inside the atom get excited. We will actually look at this prac again in one of our classes next week and look at it from the perspective of what we know now in Year 11. So, as we should know, if we pass light through a prism, we get the bending of light based on its different wavelengths. If this light has been given off by a particular atom, we will see a pattern of lines on a black background, which we refer to as the emission spectrum, like this one over here. Okay, that pattern of lines and the precise wavelengths of which we see them at is like a fingerprint for atoms. It's characteristic of particular atoms. So we can actually identify particular elements by looking at the emission spectra, and this is one of the ways that we actually work out what stars are made of and what things we're looking at up in space without actually visiting there. So hopefully we will remember that we can tell the energy of light based on its color, and you may have all heard Roy G. Biv. Okay, where red is going to be low energy and violet is high energy. Okay, so in this one we get energy increases as we go across the different light colors. So emission spectra are, as I was saying, essentially fingerprints for the elements. The pattern of lines is unique, and each atom of the same element will always produce the same emission spectra, and these provide clues about how the atom is structured and the different energy levels available within each atom. So you can see here that we have a number of emission spectra being shown as examples here, including hydrogen. And even though hydrogen only has one electron, it does have a number of different energy levels in which that electron can jump to and then come back down for us to be able to see the light from. So each line doesn't represent an electron in the atom structure. It represents an energy level within that atom. So the Bohr model of the atom, as discovered by Niels Bohr, was that electrons orbited around the nucleus in distinct energy levels. This is essentially the model that we have shown you in terms of electron configurations up until this point. So Bohr's model proposed that electrons travel in the nucleus in fixed orbits, that the orbits were at different distances from the nucleus and corresponded to different energy levels. So electrons could only occupy specific energy levels, fixed energy levels, and not exist between the two levels. So it was kind of a one or the other situation. They couldn't exist between the energy levels or have variation within those energy levels. So it was possible for electrons to move between energy levels if they absorbed energy and then emitted it to come back down. So absorbing energy pushed the electron into a higher energy level, and then it could only come back down if it emitted that energy, usually in the form of light. So these are the Bohr shell diagrams that you should be familiar with. Okay, so in lithium, remembering our first shell can hold 2, and then so it's 2, 1 because it has 3 electrons. Sodium has 11 electrons, so it's 2 in the first shell, followed by 8 in the second shell, and our valence shell has 1 electron. And then when we looked at krypton, we have learnt that it was 2, 8, 8, 1. So even though we've been putting electrons into shells, we haven't really talked about what they are. So we define shells as being regions of space around the nucleus where an electron may be found. Okay, so these are mathematical representations of where we can potentially find electrons of particular energy levels around an atom. These energy levels are given the symbol N, which relates to the principal quantum number or the shell number. Okay, so N equals 1 is the shell closest to the nucleus, and then as we move out from the nucleus towards the valence shell, the number goes up. So electrons fill from the lowest energy level first, so the electrons closest to the nucleus, so in shell number 1, N equals 1, electrons will go into there first, and then as we move further away from the nucleus, they increase in energy, so we fill those last. And when we look at this, if we're looking at plotting E on the y-axis, this means that our energy levels will increase as we go up from 1, 2, 3, and 4. These ones over here are our sub-energy levels, our subshells, which we'll come to talk about shortly. So what this means for emission spectra is that electrons can jump from one energy or one shell into another. So when it's heated or absorbs light energy or heat energy of the right amount, the electron can jump up to a higher energy level and then return. Depending on which of the energy levels it lands on when it returns, this determines the amount of energy or the color of the light that we see when it comes out. So here, if this is N equals 1 on our base level, electrons promoted all the way up to the third excited level can now come all the way back down, which would give us light in the ultraviolet or ultraviolet region, or they could drop down a little bit, emitting a little bit of light, and then drop down again, emitting light of a higher energy. Or they could come down in 3 stages or 2 stages of larger energy level. And these probabilities and chances of them coming down in these different ways are why we see so many lines on the emission spectrum, even though the energy levels themselves within the atom are set. The electrons can come down in one or in multiple stages, bouncing from one energy level to the next. And each time they come down in energy, they will emit the energy to get to that lower energy level as light. So the electron configuration of an atom tells us how the electrons are arranged in each of these energy levels and puts them in order from lowest to highest energy. Okay, the properties and chemical reactions that an element displays are dependent on the electron arrangement and the electron configuration. Because this determines their valence electrons or outer shell electrons, which are the ones that are key to the type of chemical reactions that they undergo. So electrons in the same shell have roughly the same energy and are considered to be roughly the same distance from the nucleus. So shells are our largest kind of energy grouping that we see in atoms. So as you know, you will have learnt this in year 10, that we can determine the number of electrons per shell by using the 2n squared rule, where n is the number of the shell. So if we take the number of shell, multiply it by itself, so square that number and multiply it by 2, we will get the maximum number of electrons that can be held in that shell. So for shell number 1, that means that n squared is going to be 1 squared, which will be 1 times 2 is going to give us 2. 2n squared is going to be 2 times 4, which gives us a maximum of 8 electrons in our second shell. For shell 3, we can hold 18 electrons, and shell 4 up to 32 electrons. And this goes on for n being, for any value of n, 2n squared being the maximum number of electrons that we can have. We don't have an infinite number of shells though, as we'll see when we look at the periodic table. So when we fill electron shells, we do so in a specific order, and the general rule is that we fill them from the lowest energy to the highest energy, i.e. from the nucleus out. So each energy level must be completely filled before the electron goes into the next energy level. When we look at this for sodium, looking at our typical Bohr electron configuration, sodium, of course, having an atomic number of 11, so Z is equal to 11. Z is equal to 11. This means that it will also have 11 electrons. So remembering that we put 2 into the first shell, and then that is full. Then the second shell can take 8. So that takes us to a total of 10 electrons, putting us 1 electron into the third shell. So you need to be able to write electron configurations up to element 36. So I suggest you actually practice these, particularly those ones that are over 20. So I'm going to leave this video here. And then the second video we'll look at ionization energy and subshell notation. So remember to practice those electron configurations, because when we come to subshells we're going to be adding a level of complexity to it.